you do the math, and that's the number that you report on paper. But I want to draw an important distinction, which is over here, what I call, or called effective reduction. And I don't know that this is necessarily on your cheat sheet, but I want to define that. So sometimes when we do certain things and we know or should know that they're not helpful in closing up the holes, we still have to report that in the overall mathematical calculation, but from the standpoint of having confidence that we've closed up the holes and given our customer a good part, we don't include it there. So that's why I call it effective reduction. And what I've said here on this line is that the minimum effective reduction to close shrinkage cavity is 100%. Under ideal conditions, which you certainly can have. This is one of those times where you can get ideal conditions in the forging world, would be 3 to 1. That's the absolute minimum that you're going to need. And I showed earlier how we arrive at that number, because and you'll see it on the cheat sheet that Dr. Metzloff put together, how the center line is worked 1/3 the length of whatever the die bite is that you're taking. So that, of course, means that you have to make 3 consecutive passes to get the entire length of the object worked at the center line, so that's where the 3 to 1 comes from. If we're going to have upset reduction count towards effective reduction, then we need to have at least 2 to 1 or 50%. We can do upsetting, and we do upsetting all the time at different amounts, both greater or lesser, for reasons that have nothing to do with trying to get the center line closed up. Those are reasons that we have just for creating the shape and the size that our customer is asking for. And that's perfectly fine. We just need to know the difference between the two. So are there questions on those concepts? Does anybody feel more comfortable with that material now?
Area reduction.
It is area reduction when you're talking about drawing out, and it's height reduction when you're talking about upsetting, the change in height. That's always the minimum. That's always the minimum, right? So because that assumes that you have these ideal conditions, which you may or may not have. So that's right. Yeah, right, exactly. So if you have that, then the minimum that you would use would be 3 to 1. So internally at Scott Forge, we will never supply something to a customer that has less than 3 to 1 reduction. That's our internal standard. Our customer doesn't tell us that. Some of them do, but that's what we have adopted as our internal practices. And we do that because of this, right? Also, going along with this at the same time, but not thought about as much, is the idea of breaking up the as-cast microstructure and developing a wrought microstructure. We talked about that a little bit. That is also important on a forging standpoint, but this is of, say, primary importance, and if you're getting this done, the other part will come along for the ride. So I don't have to so much emphasize both of them, because they kind of happen simultaneously. You look like you have a question. You can. Okay. You sure can, absolutely. It doesn't. The choice of order is really a function of what it is you're making, and there's other considerations that you have to be concerned about when you're making a shape. When you have when you're doing something that and you're upsetting it and you're going to shorten it, you're limited to how tall a piece you can upset. If its height exceeds 3 times its diameter or its cross section, so if I have a 24-inch square, I'm going to be limited to upsetting something that's 6 feet tall. All right, because if I go taller than that, the column will actually want to buckle. It can't support itself, right? So I have that limitation. I have to respect that, as well as all these other things. There could be other things as well that go into what I'm doing. I may be, for example, making a shape that looks like this. So if I make a T-shaped cross-section, we would call this a flange or a hub. To create this form here, this part of it would require upsetting. This part might require drawing. I'm not likely going to make this by taking an ingot and upsetting one end of the ingot and not doing any work here, because that would create other problems. So I'm going to have to do some minimum amount of drawing to get this part worked. So I might draw this down to this size, and depending on what this is in relation to this, I may be able to then put this in some kind of a tool with a certain amount sticking up above, upset it, and get this formed. I may not be able to do that because the diameter of this may mean that I won't have enough length. I'll be over my 3:1 when I go to upset this, right? If I have something small here and something that takes a lot of volume here, maybe at this diameter I need 6 or 8 times the diameter in length to create this volume. That's not going to work either. So I may have to come down to some bigger size, some intermediate size, so do a certain amount of drawdown work, put it in the tool, upset it, make this flange, then come back out and draw this down some more. So that's very common, to have to combine different things together to get to final shape.
So you can put that first part down the hole.
Yep.
And then come and upset part of that,
That's right.
so long as you can get it back out of the hole.
Well, you put taper in the hole and then it comes right out. Yeah. Mm-hmm. Yep. Yeah.
So do you, if you have like a 10-foot ingot to start and then you're making like 6-inch round pieces or whatever, do you draw and offset the entire ingot and then cut it up in pieces, or do you cut it up in pieces and then draw and offset each piece?
Okay, so as with almost anything in the world of metallurgy or forging, there's more than one way to do it. So the answer is that it depends. Okay, but let's try to. And Mike's going to kick me after class because he's been hearing that for 40 years. For those that didn't get a chance to meet Mike, Mike is a colleague of mine from Scott Forge. He's been in the forging world for how many years, Mike? 40 something? You've been forging for 40 years, maybe? 39 years, almost 40 years. So if I make any mistakes today, I'll hear about it on Monday at work. But so back to your question. I might, in certain cases, cut it to a smaller level. But I don't know that I actually have a slide on this, so I can cut right over here. When I'm forging something out, I do kind of have a slide on this, so we'll cover it after the job. Forging something, I want to draw this out to some longer length, smaller cross section. I haven't covered this yet, but this, what I do here is what makes this tall. Okay? If I want to upset this, I can upset this entire form. It would be perfectly fine to do that. Square or cylinder, because its diameter and its height are well under that 3-to-1 relationship that I talked about. But if I want to draw it out, let's just assume that the original ingot height is now laying down. So this is the axis of the ingot, right? We're going to say that's the longitudinal okay? So this is the axis of the ingot now. I want to draw this out, make it much longer, much smaller, which is very complicated to do. If I start forging, let's just assume it's not an ingot, let's assume it's a fillet. It's already got 100% closure. There's no holes in it. I can do whatever I want. Okay? So I don't have to worry about the guide lights being half the cross section, 20% rack. That's all off the table. I just want to make a shape. If I bring my die over here and I start squeezing it, I can do this, but I need to make sure that my amount of metal in this die in this case is one half, approximately one half of whatever this height is. Not because I'm trying to close up the center line or anything of that sort, because I don't want to create a situation where the surface goes out ahead of the metal. What I mean by that is this corner right here. Like the metal portion on this corner will move out like this. And I'll end up with the metal kind of out, the center doesn't come out. And if I continue to go on with this, I'll end up with a crack, right? The factory that will have some kind of crack when the factory going apart, right? So to avoid that from happening, I have to have, in this scenario, I have to have a die bite that is half the stock cross section. I think Mike can pull it off with 40%, he's really good, but typically we want to shoot for half, it's a little bit of a right? So if I have less than that under the die, then I'm going to get this kind of metal flow. Right? So the question, why this applies to your question, it would depend on the cross section of that I'm starting with. So it could be 10 feet long, or if it's a small cross section, then I might be able to cut it up in small lengths and do it done. But if I'm starting with a large diameter, I would probably need to put a lot of work into it before I cut it so that I don't run into that problem. I don't know that I turned it on, I just put it on. Is it right? Okay. Does that answer your question related to everybody else? Okay. Pretty comfortable with the homework concept. Dr. Metzloff, could you swing my camera over this way too? Yeah. Thank you. So I'm going to jump forward to where we left off last week, which is about halfway through, I think. Yes. So Dr. Metzloff, we actually need a different lecture. Yep. That's the next lecture. No, the one preceding this one.
Yeah.
Because we didn't quite make it through the last week's lecture.
This one there.
The forge technique. Yep, that's it. Right.
Around here
Yep.
somewhere.
I was just a couple slides before that, I think. Well, maybe more than a couple. But yes, I'm in
Yeah,
that.
we did these graphs.
Yeah, but I'm going to bring that graph
Okay.
back because, yeah, it is the one on.
Let me do the slideshow then.
I've got. Oh, okay. Oh, yeah, sure. Yeah. And we're going to jump this. Okay, so this was the image that I left off with at the end of class last week. We were talking about actually somewhat similar concept to the one I just illustrated on the board over there. What happens when we use a shallow draft, or in the case of, say, the forging lab that we did last week, the blow, the forge. On this side here to drive that back in before you form a crack or a seam in the workpiece. So now we were, whoops, let me see here. I want to talk about some specific cases when we might be challenged to reach that ideal scenario that we talked about, where our die bite is 1/2 our stock cross section and we have a draft that's 20. We want to achieve, but sometimes that's not feasible, and there's some situations why that might not be something we can do. Can anybody think of some ideas? Just to is, what if the ingot that we're working on is too cold? And Mike will tell you this never ever happens, but once in a while, when he's not looking, I've seen it happen. What can happen? Ingot, you get, let's say you've got an ingot. Usually you don't heat one ingot at a time, You try not to do that, it's not very efficient, so you'll have a furnace loaded full of ingots. But sometimes something happens, there's some sort of an equipment malfunction, or the furnace just isn't started when it should be. So these ingots, they don't just heat up in an hour. To heat large ingots can take a half a day, maybe a day and a half, maybe even 2 days if they're really large. So if the cycle isn't started at the right time, then when the guys are scheduled to start that job, the furnace may be behind and the work's not at the right temperature. So if the ingot comes out and it's colder than it should be, you may find it difficult to achieve that ideal situation with the press capacity that you have. So if that were to happen, the appropriate thing to do would be to reheat the material and wait for it to get up to temperature. In a manufacturing environment, people are not paid to wait for things to happen. They want to get work done. And so there's an incentive to keep going on the work, even though it might not be exactly where it should be temperature-wise. So we have to make sure, as engineers, that we help our colleagues understand the importance of having things at the proper temperature and help them understand what can go wrong when things aren't at the right temperature. So in this scenario, the right thing to do is to reheat the workpiece. You could also have a situation where the piece of steel that you're working on is just too large for the press that you have. Now, in an ideal world, you would not ever let this happen. You would have enough resources in your organization that you can shift that workpiece to some other facility, some other press, and have all the force and tonnage that you need. But again, in the real world, that doesn't always happen. Sometimes presses break down and you're forced to use the remaining presses that are available to you. So what do you do in that case? Well, certainly we make sure that the ingot isn't too cold, but we're still faced with this idea that it's just too big to get effective reduction from the very beginning of the forging process. What we're going to talk about is, in that case, we will consciously make a decision to use a less than ideal practice. We will take a die bite that's narrower than what's ideal, with the understanding that it's not going to give us effective reduction. It's going to give us mathematical reduction. It'll give us an observable change in the size of the part, but it's not going to be effective at closing up the holes that are inside this part. And we just recognize that that's going to be the case, and that's okay, as long as we move forward with that understanding. Once we work that piece down to a small enough cross-section that we can get effective reduction, then we can start counting it towards our goal of closing up those holes. So what we would do in practice would be to bring this large cross-section to a press that's really less than ideal. We would forge it, and we have to be very intentional when we stop forging. Again, there's a tendency for operators to want to get as much work done as they possibly can in the shortest period of time. That's just how they're efficient with their time and energy. So what they'll often do is they'll keep forging until the piece is too cold for them to really work it anymore. And then they'll put it back, and then they'll let it reheat, and they'll bring it out. And so we have we call those multiple heats. Every time we go in and out of a furnace like that, that's a heat. So they'll have multiple heats. What can happen is that the work they do in the first heat gets them to a size that's so small that in the next heat or two, they don't have enough work left to do in the part where they can get that 3-to-1 effective reduction. So it's really important that they recognize that this condition exists, that they're going to take this step on purpose, but then they're going to stop. And the part might be hot enough they could continue deforming it with this kind of a practice, but they're going to stop at a bigger size, put it back in the furnace to make sure that when they come back out, they can get that 3-to-1 effective reduction. And as long as they do that, it's perfectly fine, and we can still make very high quality parts that achieve all the goals we've set for ourselves. And that's this 3-to-1 this is my longhand way of saying effective reduction. So, kind of in summary, we would say that under ideal circumstances, only a fraction of our W, our die bite, is being worked at the center of the cross section, and we said that that fraction mathematically is 1/3. Right now, we could make that bigger by using a deeper draft, using a bigger die bite, and we would certainly encourage our operators to do that. But for purposes of having confidence that we know we're closing up all those holes, we want to work in the world of the ideal equation, because it's easy. It's easy to remember and it's easy to figure in your head. So it's essential that our die bites be overlapped. We talked about that last week. If we're doing something that's long, we have to overlap from one side to the next, one pass to the next, so that we hit the spaces that didn't get worked along the center line in the next pass, and then in the third pass, we have to make sure those things are overlapped. If we don't do that, we'll end up with areas that are left with these shrinkage cavities along the center line. I've seen that. I've seen results from our non-destructive evaluations where they do an ultrasonic test and you've got, you know, a section that's nice and good, there's no indications, and then a section with indications, and they're very evenly spaced down the length of a bar. And right away I know that there was an issue with the overlapping on that bar, and that's why those holes exist there. So if we're not effectively working the cross-section, we can't assume that this 3-to-1 reduction will eliminate our cavities. If we're effectively doing that, then 3-to-1 is an excellent mathematical relationship. But if we're not working the center, then we can't use that 3-to-1. And so I emphasize this because if you go out and pick up a generic forging book, there's some that are published by the FIA, Forging Industry Association, that are just intended to give the purchaser of forgings a general understanding of what's done in the open die world. That book's going to say, you know, typical work is 3-to-1, and it's typical. But what they're not going to tell you is all this other stuff about the difference between mathematical reduction and effective reduction, and that's something that customers are also typically not going to know. This is the kind of thing that you pick up when you're in a forging company, and that's what the forging companies should know and should be implementing in their shops.
What effect does the draft have now?
So if you increase the draft over the 20% and keep the die bite at least 1/2 of the cross section, then L will get bigger.
Right.
I can't tell you how much bigger because I don't know.
Okay.
But it will get bigger. So if I'm, you know, when I'm providing instructions and guidance to my colleagues who are operating the presses, I'm going to say, here's the minimum, but if you can do more, by all means do more, because that's going to give us that much better assurance that we've given our customer the kind of product they're looking for. Right, you have to balance that with the risk of lapping. So as long as you're not going to lap it, which is, it's usually pretty evident when you're in the midst of forging, it's very evident if you're at risk for having that happen. So that's one that the press operator is really, that's really his responsibility to avoid that. But it's not hard to see that could happen, and so he can adjust his technique, you know, in an instant, because the way our presses are set up, it's all done with the operator has control over every push of the press. I want to say it's a little bit like a video game. It's not exactly like a video game, but he has a joystick that he moves forward and the press comes down, and he pulls it back and the press comes back up. And so for every time that he wants to come down, he can do that, so he can see in real time, I'm getting to a point where it's too deep, I'm going to pull back, so that doesn't happen. Yeah. One last little bit with respect specifically to rectangular ingots. We talked about these a little while back. So we do get rectangular ingots from time to time. They have a common, you know, they're used for certain situations. When you're dealing with a rectangular ingot, it's a little different than having one that's cylindrical or square, because it's got, you know, what we would say a high side and a low side, right? It's a rectangle. So if I've got a rectangle, I have a shrinkage cavity that's not circular. It's actually more of an ellipse. So you can imagine if I took that rectangle and I stood it up so that the long edge is vertical, and I push on that, I'm going to have the ellipse wanting to get shorter and fatter, right? I kind of showed that in the upsetting of the upsetting experiment that was done, where they had the holes drilled down the little blocks and they upset. The same thing happens in a rectangular ingot. So if we're able to, again, this comes back to equipment capacity, but if we're able to do it, making our first pass on the low side of the ingot is going to be preferred, because it's going to help close that shrinkage cavity more rapidly than starting on the high side of the ingot. Sometimes we're not able to do that due to equipment limitations. And again, that's okay as long as we understand that and adjust our process accordingly so that we get the effective reduction at the right place in the process. So something that we can do, let's if we've got an ingot and it's too big for our presses. Hopefully we've recognized that before we put the ingot in the furnace and we have a chance to come up with a new plan to make that part. We may be able to make the same part from a smaller ingot by upsetting it to get a larger cross section and make that large part. And that can work out really well. If we do that, how much upset work should we do? This is a class participation question.
The question is, are you trying to close up the porosity or not?
I am. Yes, I am. Starting with an ingot, I'm going to do an upset. How much upsetting should I do?
It's on your cheat sheet.
It's on the board. Right, at least 50%. At least 50%. Yep. If I don't...
I have a slide that I can show you guys later on where we upset some little 1-inch diameter rounds. Then we section them and look at the grain flow on the inside. And you can see where it's just starting at 50%. It's just starting to change the structure at the center. Then at 75% or something like that. As you can see that it looks like it's collision course going on in the middle of that.
Right. Yeah. Yep. So we said 50%. That's good. And we talked about why that is. Okay. So in summary, if when we're cogging ingots and we're trying to close up shrinkage cavities, if our die bites are too small, then we're not going to work the center line, and we'll be left with unclosed holes in the center. That's a problem. Short die bite won't work the center of the ingot, and it doesn't matter what the temperature is. So that is to say, I can have my ingot fully heated all the way through, maybe even overheated. And if the die bite's too short, I'm not going to work the center. You remember I showed this last week with the illustration of a cutting tool that has only maybe 2 or 3 inch wide cross section. You put that on top of a piece of material and you can push it through. And the little friction pyramid that's made is so short that you'll never get it to interact with the center before you cut the piece in half. So that's an illustration of having a die bite that's too short to work the center line.
You could do all of that work though on one side and just make a flat rectangle, right? As long as you have to do the reductions and calculate it as you go, but could you just do it all from one side?
Could I do it all from one side?
Let's say I'm trying to take an ingot and make it into a flat plate. Like a square ingot to go to a flat plate.
Oh, you mean without rotating the?
Yeah.
So if I just want to make a plate, yes. Yes, you could. You sure could, right? And that's actually kind of in our homework a little bit, because that's really what we want to do with the little ingot that you have. You want to take that, and eventually you do want to make a plate out of it. And so you absolutely can do that. And in fact, steel mills that make ingots that go into plate rolling processes will make big rectangular ingots for that very thing. And they know that they're only going to work the metal from that one side. They're not going to come at it from 90 degrees. So yes, you can do that. You still have to offset your bites from one pass to the next so that you work the center line all the way through. But yeah, you absolutely can do that. Any other questions? We also talked about shallow drafts, and I illustrated that through making that kind of that dog bone shape. If you have a draft that's too shallow, or if the metal, if you don't hit it hard enough, you won't work it all the way to the center. So we see that we need both the draft and the die bite size. Both of those together, they have to be, they work together to get the metal at the center moving and getting those holes closed. And just to close off this section, this is not consolidating anything at all. This is just a really, really big forging that I thought was a fun image. This want the qualities that go along with a forging, which means they don't want any holes left there.
Yeah, you want 1 second?
Sure.
That should be it.
Okay, good. All right, so questions, comments? No? You sure? Yes? Yes? Oh, okay. Man, I had my hopes up. All right. Okay, here we go. So we were talking about having the importance of closing up holes that exist in our raw material, in the ingots. We're going to change our perspective now and assume that we have done that, we've done that successfully, and we have a piece of material that is free of holes. It's as good as we can possibly make it. Now we're going to talk about how do we keep it good and not mess it up, because not only do we have the capability of closing holes, we also have the capability of creating brand new holes. And we're going to talk about how to prevent that. So we get these holes in certain in material that's already free of holes through a tearing process, or it happens by shear, or also from tensils. These two here: centerline shear stress, centerline tensile stresses. And if you happen to have some pre-existing defect along the center line, that could also serve as an initiator for this center line tearing. That could be a few different things. You could maybe you didn't close up all the holes and you thought you did. Maybe you've got some raw material issue of some inclusions. Maybe you have some very large grains at the center that are interacting with the metal in a way that's causing some unusual stresses. So these are the three primary causes of centerline tearing, and that's what we're going to really talk about trying to avoid right now. So centerline shear stresses happen primarily when you have something that is a square or a rhombus, and you're trying to make it round. So if I had a square and I was going to make an octagon out of it, which is the normal step of going from a square to a round, pretty typical. If when I go to do that, if I don't get that square with the corners perfectly lined up vertically underneath my two dies, and I come down and squeeze, instead of just having this thing fall over and lay on its side, which you think would happen, there often is enough friction between this surface and this surface to lock the piece in this position and then force this half of the metal down and this half of the metal up, and you get a shearing stress at the center. When that happens, you really increase the risk of tearing. Certain grades are much more sensitive to that than others, and we'll get into that in a little bit more detail momentarily. Here's kind of what happens in that scenario if we think about it with respect to that friction pyramid that we've already talked about. You can see that instead of having the two friction pyramids lined up with one another as we showed before, they're now offset from one another, and we get again, you get a shearing action as they slide past each other. This tensile stress that I mentioned can happen whether or not you have things properly aligned. Let's just assume this looks like it's a little bit out of alignment, but let's assume I had it fully lined up just fine. When I squeeze, I'm going to have the two dies coming together, and of course I'm going to have metal moving out to the side. So that's going to put a tensile load on the center. The magnitude of that tensile load is going to be a function of how much metal I have under the die being deformed in any one push. The more metal that's under the die, the more metal is going to spread to the sides, and the bigger the tensile load will be. And last week I had a a sample piece, I believe I brought in, that showed that on one chunk of metal with a wide die bite, the metal spread a whole lot laterally, and on the other end of the piece, the other half of it, I had worked with narrow die bites, and it had spread, but much less, and most of it had gone out and elongated. Now, I did that with a hammer, but it works the exact same on a press. So we need to understand that metal moves differently depending on how much we have under the die, and we need to control that depending on what we're trying to accomplish. So if we're trying to prevent a high tensile load at the center line, then we need to limit how much metal is under that die. Some factors that can contribute to how much stress we have are composition size, temperature, the amount of metal under the die, how much penetration we have, so how much draft we take, and how fast we push. All these are variables that we can control, but if we don't control them and we just kind of take a random approach to how we're forging, sometimes we'll make great forgings and sometimes we'll have some that don't turn out so well. So we need to understand how to control these things. I'm going to go back to a graph that we looked at last week. This was the hot twist data that shows number of twists to fracture versus temperature. And remember, we spent quite a bit of time talking about how we arrived at using these different temperatures. And we said, here we've got a material that has a lower melting temperature than many of the other materials that are illustrated on this graph. So it starts to show failure at a much lower temperature than these others. Okay? So we also talked about how this grade here, the 1015 and the 1117, so these two are nearly identical materials, with the exception that this one here, the 1117, has sulfur added back to it, which is great if you're a machinist. It allows you to use faster speeds and feeds. Machinists like that. But from a forging perspective, what this shows me is that I'm going to be able to, how should I say this? This material here will be able to withstand a lot more centerline shear and centerline tensile stress than this material here. So as a forging operator, I need to know what I'm working with and understand how to adjust my technique based on the material type that I have. Things that I can do with this material, I better not do with this one, or I'll end up with a part that's scrap. Same with these two here. These were the two martensitic stainless grades. We had the T416 and T410. Both of these are very low on this graph. We can see that they're very low, again, in comparison to, say, these materials here, which are low alloy steels. You can do a lot more here than you can here before you cause a problem. So again, you have to be aware of the materials that you're working with and tailor your procedures accordingly. So summarizing that graph, we see that the hot ductility decreases as temperature goes down. It gets harder to move metal as it gets colder. Hot ductility also decreases when we put sulfur in steel. And then, of course, we put sulfur in really primarily to aid in machining. You'll see, and we may talk about it in a later lesson, we will put very small amounts of sulfur in many of our grades, not for machinability, but to help with a different problem. But that addition is very low, and that small amount of sulfur really doesn't cause this problem. It's when you get to a high level of sulfur where you have a lot of manganese sulfides that are formed that you have problems with hot ductility. We also can see that hot ductility decreases with increasing hardenability. Another way of saying that is, as the alloy content goes up, the hot ductility goes down. Yes?
So I've seen a lot of food machining alloys with lead.
Yes.
Is that equally forgeable, or does that start getting your grain boundary melting?
Well, it is something that can be hot worked, but we don't work it at Scott Forge. So I can't tell you from any personal experience about that. My assumption would be that it would be at least as difficult to work with as the resulfurized materials. I don't think that you find a lot of the leaded steels around anymore because of the environmental issues associated with getting the lead into the steel and then how you deal with the chips and so forth afterwards. Leaded steels used to be really common because they were easy to machine. They have worked the steel industry has worked a lot to find alternatives to that. So the use of sulfur, which doesn't have the environmental problems. Bismuth is sometimes used as a substitute for lead. You also, I mean, there's one grade I know of, sort of the one that's kind of uses the gold standard for machinability, is called 12L14, which has both lead and phosphorus in it. Well, I mean, it's great for machining, terrible for mechanical properties, and probably not that great for hot working, but if all you needed to do was machine a widget, it's great. And I think, I mean, the material is still available, but I don't think it's nearly so widely used as it once was.
They usually surface harden it, or, you know, case harden it or something like that. You're going to machine it really quick, and then it's case hardened.
Yeah, yeah. And then lastly, hot ductility decreases as the overall alloy content increases. So these two are related but not identical, because you could have things that have high alloy content but not necessarily high hardenability. And we have a whole other section of our class that's going to talk about heat treatment, response to heat treatment, and hardenability. But I would hope that you guys have all at least seen that term and thought about it a little bit. Is anybody like totally confused by that? Yes, no, no,
The
okay.
geometry hardenability thing.
Right, that's what we're getting at. So,
The diameter gets
Yep.
bigger as the hardenability increases.
right, yeah. So we'll cover that in significant detail in some future lessons. So a decrease in the hot ductility means that whatever we're dealing with is going to be more sensitive to this centerline tearing. That means we have to be extra careful with it. Doesn't mean we can't forge it and we can't make things out of it. We just have to be very careful how we do it. We're going to have to be really careful about minimizing that stress. So let's talk about how we do that. First and foremost, if you're making a square, make a square. Don't make a diamond. Don't make a rhombus. Make a square. Some of you may have experienced that can be a challenge when you were doing your forgings last week, because we were trying to make something square and then eventually change its shape. And some of you I know had issues with that becoming a bit of a diamond or rhombus shape. That happens out in industry too. So we have ways to prevent that or to keep that from happening. Mostly that has to do with the skill of the person who's operating the manipulator. And so it comes with practice, but you practice and you get good at it. So that's the first thing. The second thing is use small die bites. So this is the opposite of what I was talking about 10 minutes ago, but it's very important. You use a small die bite. Now that's a relative term, right? Small and big really are in relation to the kind of equipment you have. So if I'm making something that's, say, 15 inches in diameter with dies that are 30 inches wide, that's not really small. That's a half the size of the die, okay? But if I'm making a 3-inch diameter and I've got 30-inch dies, that's a big difference, 10 times, right? Now that is small in relation to the size of the die. If I make that same 3-inch diameter at home on my forging hammer, which has a 4-inch wide die, now it's big again. So it's a relative term. So we have to recognize that as we're applying these techniques in industry, because we have lots of different sizes of equipment. I can change dies, I can change presses, so I have to make sure that I pick the correct combination of tools for what I'm trying to do. The same with the drafts. Shallow, again, is in relation to what? To the size of the work you're doing. But in general, we want to keep our die bite width about the same as the workpiece cross-section or less when we're dealing with these, trying to prevent the centerline tearing. And so you may have realized that as we go through a job, we may start with an ingot, be using a very wide die, a deep draft practice, and by the time we're done, we're back here to using shallow dies, or shallow drafts, narrow dies. So depending on where we're at in the point of manufacture, we have to be able to pick one technique over the other. For a forging, like what I call a spindle, a step shaft, something that has multiple diameters in it, there may be a tendency to want to define where your transition is going to be and then go right up to that transition point and take a nice big die bite right there in the transition. there can be some reason for that. It can be easier to control metal flow, easier to keep the part straight. There may be a tendency to do that. But if I have, let's say I'm doing that. Let's say I've got maybe this example that I put up over here where we have this flanged forging and we've got a journal coming off of that, and we said that one scenario was such where the journal would have to be made at a larger diameter than its final diameter because of the volume of the major diameter of the part. The tendency may be to get right up next to that shoulder and start to squeeze that down to bring it out to make the final diameter of the journal. And I could do that, but let's just say that my journal is 4 inches in diameter and I've got a 20-inch die on the press. Well, it might not be wise to do that because I'm going to run the risk of creating a large tensile load in that area and could cause the part to rupture, to tear internally. So it would be much better to start on the end of the journal and work up towards the shoulder so that I can keep the die bites narrower so that I reduce the risk of that tensile load. All these things have to be balanced with making sure they're not too narrow so I don't create the other condition that I illustrated over here, right? So I have to have enough metal under the die so I don't have this happen, but not too much so that I cause a tear. So things are always competing with one another, which is true in all aspects of metallurgy, right? Mechanical properties, you always have one thing that's being balanced with something else. The same with forging. We're trying to accomplish one thing, but that's in balance with something else. We want to make sure that when we do our corner breaks, this is when we go from a square to an octagon. We call that, at least at Scott Forge, we call that breaking corners. When we do that, we want to be careful how we go about doing that. We may need to make multiple passes on the corners. If we broke the corner down to the final dimension all in one push, that might be too deep of a draft. It might cause a large tensile load on the center. So we may need to make 2 or 3 passes with shallow drafts down those corners to make sure that we don't create a high tensile load in the center. Another thing is, at least at Scott Forge, a common practice has been to, if you've got, let's say I've got a long bar or long shaft, and I'm going to make it from a square to an octagon. It's quite common to orient the corners upright, you make your first push, and then you rotate 90 degrees, and you make your next push, and then you index your machine forward, you make your next set of pushes, rotate, and so that you're always hitting both sets of corners before you index your machine forward. The problem with that is every time you rotate your part, you run the risk of having the corners misaligned. If you get into a rhythm where the person operating the manipulator, and he is always working independently from the person operating the press, because there's 2 different pieces of equipment operated by 2 different individuals, you run the risk of having the press come down out of sync with the piece being rotated, and now you could create that, you could twist it, but you could also create that shearing action at the center line. So on materials where we know the material is at high risk for this problem, I'll write specific work instructions to say, don't use that practice. Start and work from one end to the other down the full length of the part, then make one rotation and work the full length of the part. And then if you need to make multiple passes, that's fine, but in the end you only have 6 or 8 total rotations instead of 50 or 60 or whatever the number may have been. The trade-off is that the manipulator operator will tell me it's harder to keep the part straight when I do it that way. And he's right, it is harder to keep it straight. So we have to, again, we got to balance, we have to work together. I have to respect the challenges that he has as an equipment operator with what I'm trying to accomplish. I mean, this is also his goal as well. He wants to make good parts, but we have to work together on how do we accomplish that. So sometimes we'll compromise and maybe we'll make a first pass, light pass, where we do rotate after each push of the press, because that helps it make it a little easier for him to index the part forward, but maybe the subsequent passes are done the way that I want so that we're not overloading the center. And a lot of times that works out well, having that compromise approach. Just as a side note, when you're in engineering and you're in manufacturing, it's often necessary to be very open to hearing what your colleagues who have different skill sets and experiences are telling you, and not just take what you know as an engineer and say, here, you have to do it this way. You may really believe that you have to do it that way, but you need to make sure you listen to your colleagues and understand their point of view. And in the end, you may still say, you know what, it's important that we do it this way, but you also then need to tell them why so that they can understand, because you may be making it much more difficult for them to do their job. And if you're going to do that, they're going to get frustrated. So you need to help educate them so that they know why it's important that you just made their job take longer and be more difficult. Okay, sometimes we, actually this is exactly the scenario I talked about just a minute ago with that hub forging. We would call that a tool job, where the journal is contained in a ring while we create the major diameter. Then we pull the part out and draw out the minor diameter. And so that ring is just a tool. And we use tools all the time for creating all different kinds of things. So when we're in those scenarios, like I talked about before, we want to make sure we keep our workpiece hot. We want to start at the end of the journal, not at the shoulder, so that we're not taking a really large die bite and causing a big tensile stress right in front of the shoulder. So we use small die bites and keep our corners properly lined up. Now, there is a way that we can reduce our risk of centerline tearing using special tools called swages. These are tools that, this is a cross-sectional view, and when you use a tool like this, it applies force to the part at an angle rather than straight up and down. You've got force coming in at 4 positions at an angle, and all of that's pushing towards the center. So when you're using tools like this, you eliminate the risk of that shearing action at the center line. So we do have some tools like this that we use in certain situations. The particulars where we use them are on products that are from 3-inch to 7-inch in diameter. And we've got special swage dies that we can install on the press and use for that scenario. We also have a unique piece of equipment specifically for making bars, which allows us to take an octagon that we forged on the press and roll it on a rolling mill that has the rolls are shaped like this. Rather than being true rounds, they're elliptical, so not V-shaped like this, but they're elliptical, and they do the same thing. And that rolling mill gives you the same end result as a swage, but it gives you a really clean surface, and it eliminates the risk of that centerline shearing action that you would get if you tried to make that round as a press forging on 2 flat dies. It's a great machine for bars. We can't really use it for anything else, but we do a lot of bar work in that shop, and so it's ideally suited, especially for the grades that are really prone to that centerline tearing. So some of your stainless grades, your resulfurized grades, it's an excellent machine for that.
So that's just a die that's shaped like a V. It's
Yep.
not like 4 coming out at the same time.
Correct. It's just in this case, it's just a top and bottom die that's shaped like a V. There is equipment in the industry that does what you're talking about, and I illustrated it in our very first lecture called a radial forge, and it does have 4 independent tools that come in simultaneously, and it also has that advantage of not having any centerline shear stress. Again, it's a very good tool for that type of work. So we just talked about that. Here's an example. This is a press over in England at a company called Sheffield Forge Masters, and you can see they're using these V-shaped tools to create a round cross-section. You can see if you look carefully, there's a much larger diameter back there. So I don't know what the part is they're making, but it's just an image that illustrates that concept in practice. So questions on that? We kind of covered 2 very different aspects of forging today.
So that would be a good set of dies to have for going from square to round.
Yeah, or mostly more like octagon to round, because you're still going to get your initial, rough round or rough octagon with flat dies in most cases. Yeah.
What's the smallest size parts you guys do?
The smallest forged cross sections that we typically would produce are going to be around 3 inches. For us to get any smaller than that is really difficult to hold on to, unless you're maybe in our hammer shop where they do sometimes hold things with tongs. But most of the work in our shops are done with larger machinery, and it's just difficult to hold anything smaller than that. It's also difficult to increment your machinery at such fine increments to prevent tearing in a small cross section like that. So if a customer wanted something like, say, a 2-inch round bar, we'd probably forge it at like 3.5 and machine it down.
Okay.
Yeah.
So like smaller stuff like wrenches or gears or whatever would be done in like a specialty shop?
Right. So if you're, like those would be done, a lot of them would be done as closed die forgings using different types of equipment, hammers, or there might be presses, but they're going to be different kinds of presses. Yeah, we don't have any raw material that's anywhere near small enough to do that kind of stuff. So every once in a great while, I'll see something super small, and I'll be kind of like, why are we making that? And the answer is that we may have a customer that's just, usually it's a military customer, then they're very comfortable doing business with us, and it's just easier for them to come to us to have that thing made, even if it costs them a whole lot more than it is to go and qualify some other supplier. I'm thinking in particular about, do you know what a key is that would go, say, in a motor shaft or something like that? All right, so if you've got a gear on a shaft, it's often held in place with a piece of square stock. The shaft has a square groove, and the gear has a matching square groove, and then that key piece of square stock goes in between the two and locks them so the gear can't rotate on the shaft. We made one of those for a military customer that was, I think, about 1 inch or 1.25 inches square, and about, I don't even think it was 1 foot long. Well, it's a big key. It's a big key, right, for some big thing, but the piece itself was only a few pounds, right? And I'm sure that we forged that at a much bigger dimension. We probably were required to test both ends of whatever the forging was, so we probably had 3 or 4 or 5 times more metal just in test material than the customer actually received as a usable part. That's super unusual for us to do, but it was for one of our Navy customers that, again, we're qualified to supply a lot of things for them, so it just made sense from their perspective. And that piece of steel, you could have gone to probably any industrial warehouse or tool catalog and bought that same thing for a fraction of the price that we charge the customer. But that customer, being a military customer, wanted certain tests done that you wouldn't be able to get done by going through this typical industrial supply catalog, so they come to us for that.
Cool.
Yeah. Any other questions? No? All right. We have completed our sections now on ingot forging and on dealing with small cross sections. It's 4 o'clock. It's a perfect time to stop today and go down to the lab and do our knife forging, I think.
Just so you know, we are in the process of rebuilding, and actually I want to show that.
Okay. I'm going
I don't know if I
to
can.
stop my
Project that.
stop my video. What?
Yeah.
Well, the homework isn't turned in yet, the one that we talked about today.
So the homework you guys are doing, I think I made it due for Tuesday.
On the point, and that's not going to remain that way. I'm just shaping the blade right now. Okay, so we'll reheat that. And again, just keep in mind that we're dealing with small cross sections that should heat fairly quickly once our forges are up to temperature. So don't let the pieces sit. Pay attention to when they're hot, pull them out, work on them, reheat them. Or if you need to take a break, whatever, pull them out, set them down so that they don't oxidize away. This is going to be particularly important as we thin our blades out, because now they're going to get quite thin and they will oxidize very rapidly if we're not careful. I've got enough heat just to finish off my point. This is certainly not as hot as it could be, but for what I'm doing here, it'll be fine. So I'm going to finish the point and kind of refine that curvature a little bit. 3/4 of an inch longer than it was to start with. The next step is going to be to taper the blade from the back of the blade, from the shoulder to the tip. And making that taper is basically the same as making the taper that we did on the handle, except we're going to try to maintain the width pretty much, this profile that we have here. We're going to do that, we're going to make that taper because it gives us a little bit of length, but also when you think about a knife, you want it to cut easily. If it's too thick, it won't cut very well. So we're going to get the profile to where it'll actually be a better cutting instrument or better opener. To do the tapering, it's the same as what you did last week. You put more blows on the end that you want thin and fewer blows on the area that you want thick. The blade will come out with a large sweep to it. That's okay if that's what you want to make, but in this case I don't want to do that. So I need to step over here to grab the tool. So this is a swage. This one is one that would normally be in an anvil, but because we don't have an anvil of the right size here, I'm actually going to use the vise to do this. I showed a schematic of how a swage could work in a press or in a big forging hammer. In an anvil, you would use a similar tool, and quite often you'd have a matching tool that would have a handle on it called a top swage. And so if you were forging in a situation where you had a partner, one person might hold the top tool, and the other person hold the work and swing a hammer to shape it. So with the edge up, I'm going to put this across the width of the swage. I'm going to hit down. I'm going to move it back and forth so I don't make a big dent in the back of the blade. It's going to twist and get kind of ugly looking, and that's okay. So it looks kind of ugly, but that's fine. I'm just going to flatten it out. Okay, so now it's been preformed. Maybe not enough. I don't know. It's kind of hard to judge that sometimes. But this will become my cutting edge, and this is the back of the blade here on this side. So the next step is to start forming the bevel. The blade will straighten out. As it straightens out, I'll probably stand it up on my edge a little bit to refine its profile, because the profile is a little bit rough right now. I might switch to a little lighter hammer for some of that, so I'm going to grab one of my smaller hammers before I start. No, they're both fine hammers, Blake. All right, now when we forge this bevel, we're going to be working on the edges of the anvil. We're going to start on an edge. In my case, as a right-handed blacksmith, I'll start here. I'm going to hold the workpiece at a little bit of an angle and the hammer at a little bit of an angle. I'm going to work on the edge. Work right along the edge, and then I make a pass just up the edge. Now I want this to be even, so I'm going to come over to this side with the same thing. Okay, so now, you can see we have our edge starting to be formed. It's not perfect yet. The edge, the bevel that I forged, you can see only is about 1/4 to 3/8 of an inch wide. I need to work my way up the blade so that I don't have an abrupt taper. If you have an abrupt taper in a knife like that, it doesn't really cut very well. So we'll make that taper more gradual. We try to work both sides of the knife to keep the bevel centered and even. There are styles of knives where the bevel's all just on one side. Nothing wrong with that. This time I'm trying to make it even. Now, I'm getting quite thin, so I'm going to get, especially the edge will heat up really fast. So I need to pay close attention because I just don't need very much heat. The longer I leave it in the fire, the more oxidation I'm going to have. Yeah.
Can you define what the bevel is?
I will. In fact, I'll draw it in a minute. bit of a wiggle where it didn't kind of fill out right there, so I may try to either pull some metal into that area or push some metal back down. I'm going to set this aside. I'm not going to heat it now because I want to answer your question, and it's going to take so little time for that to heat up that we can do it after I'm done. The bevel on a knife or any other cutting tool, all right if I erase
Yeah,
this?
so you can erase the new up the right upper right hand corner.
So, think about a knife, you look at it from the side, looks like this, and ours, you can go back out with a space like this. So look at this from an edge view, we have something that looks like this. It's roughly triangular in cross section. So this is the bevel, right? If I started off with a rectangle or a square profile, and I've changed that, and I've done this. You can have knives with lots of different profiles here. This one, as I've drawn it, that relationship would be really blunt. It would be like what you use for splitting wood or a splitting ball. What we really are looking for in a knife is something probably more like this, pretty gradual. Sometimes you'll see bevels that go from all the way from the edge to the back. Sometimes you'll see the back is a little bit square, and then the bevel comes down like this. That gives you a lot more strength if you're in a bending kind of environment. Say if you're making a cavalry saber or a cutlass or something like that. Sometimes you'll see blades, this is real common on kitchen knives, where the blade is actually, instead of a triangular taper, it's got a curve taper to it like this. This profile is not really generated by forging. They do that with grinding. They call that a hollow ground knife. It makes for a really thin profile that cuts really well, but it's not going to be as strong as something like this one here or this one here. Some knives or cutting tools have a profile that's actually a little bit more of a convex profile like this. This tends to be more your chopping or real heavy duty type of instruments. So what we're making is a fairly small tool that's going to be for light duty applications. So we're going to be shooting for something kind of like this. Remember that you can combine forging and grinding or forging and filing to get the final profile. So how far you go with forging is really kind of up to you and what your comfort level is. Any questions on that before I move on to the next step? No? Okay, I'm going to take this off. Yeah. Thank you for asking. got a little bit of a curvature if you look close. I can straighten that out, no problem. So I'm going to go ahead and just clean that up, that little wiggle. Now all I'm going to do is make sure that my blade, when I look down it this way, it's not wiggling like that. I want it to be flat. So I'll just look for any spaces that seem a little bit out of straight and try to true them up. At this point, you're doing so little work, you don't have to have it red hot, really. You can do a lot of this fairly cold. Be hard to see, but right at the very tip, there's a little bit of a twist. If I get it close, you guys see that? Just got just a little bit. The tip's just a little bit out of alignment with the rest of the blade. So I would like to take that out because when I go to put an edge on there, when I go to finish grinding, that little bit of twist will require the grind off the metal like I get out. I'm going to try. Take it out. I don't know if I'll be able to get it. I don't need a lot of heat. It's certainly going to not take very long to get hot. Bending forks come with shanks like this to go in vices or in anvils, but you can also get them that are forks on the end of a handle so that you can apply leverage with the fork itself. We'll also possibly use some tools called scrolling tongs. I'm going to step over here and grab a pair in case I need them. So scrolling tongs are not really used for picking up work. They're intended for bending, for bending curved shape, which is what we're going to do here. And they have radius jaws, so that you can, almost like a pair of needle nose pliers, really. In fact, sometimes needle nose pliers are a better tool for this operation. So here we go. Now, I have the edge facing towards me. I'm going to put this in, and I kind of have to eyeball about halfway. And I'm going to go a little bit, I'm going to pull out a little bit more metal than halfway towards me. But I didn't get myself enough. You see what happened? I've got too much metal on this side. So I'm going to open it back up. Just do this. You can take the hammer and quickly straighten out that little kink. On this side of the bending fork, so that I can get that little hook to come into the shoulder. And if I actually have a little bit too much on this side, it's kind of okay because I can actually force more of it around the curve and get it to move in where I want it to go. Give it just a minute longer to heat. Towards me this time. It's still a little bit off. So I will open that back up. Try it again. That's interested, tomorrow there's an organization called the Upper Midwest Blacksmiths Association, and they have little get-togethers about every 3 months. There's one tomorrow down in actually just south of Clinton, Wisconsin, in South Beloit, Illinois, which you know where Jim Ryberty's shop is at. That's tomorrow. You can make it anyway.
What are you guys making there?
Well, it's really a demo, and I don't know who the demonstrator is or what he's going to be showing, but usually it's a bunch of guys, they all get together. Sometimes, if the weather's not too bad, sometimes Jim will have like 80 people out there. And the demonstrator's really the only one forging, and everybody else will watch or hang out and visit. Typically there's people that are selling equipment and other things, so Jim's got a pretty decent sized shop to house everybody for these kind of events. And I wish I had his address. I don't, but if you go online, you can find the Upper Midwest Blacksmiths Association website. It'll give you the address of where he's at. It's really close to Clinton. I mean, of course, you've been there before. So now I'm a little bit short, but that's okay because I can hit this curve and I can force the metal around the curve and make it flow, bend in right into that corner. And now I have to decide if I want that to be as wide as it is there or if I want it to be a little narrower. That's going to be unique to each person. I'm guessing for me that's a little bit wide. So what I'm going to do, I'm going to hold this straight up and I'm going to hit right here and narrow that up a little bit. Maybe just a little bit more.
basically all there is to it. Now, I can see a few things that I might do differently on this one to try and improve it. I would personally try to take that out, and to get that out, I would actually have to get that out before I bend it, so I'd have to unbend the handle and work it again.